Welcome back to multivariate calculus. In this video, we're going to be looking at line integrals for scalar functions. Before we get into the actual content here, let's unpack that title a little bit and figure out what we're talking about. Right. First of all, when I say line integral, I don't necessarily mean straight line. What I mean is one-dimensional. So sometimes instead of calling this a line integral, we'll call it a path integral. Those two terms are used interchangeably. More calculus textbooks call them line integrals. Path integrals is a little bit less common, but means the same thing. I think path integral is a little bit more evocative because one of the key things we need is some parametric path. We'll define it using R, which takes a scalar value, probably t, and will spit out either 2 or 3 dimensions. For convenience, we'll look at two-dimensional paths for right now because it's a little bit easier to draw and see what's going on. And then, of course, we also need a scalar function. So some function f, which maps, we could use 1, 2, or 3 variables. One variable is very boring. So since we use 2 variables right there, we're going to use 2 variables here as well. So from r squared into r. All right, so a function that takes several variables, spits out one output. That's what we're talking about when we say a scalar function. And the key idea here is that instead of thinking about this of f of x and y, we're going to think about this as f of r of t as a composition and try to figure out how these things are related. So there's the big idea. There's the overarching idea of what we're talking about here. Instead of thinking about an area and thinking about our two coordinates as being independent, we're going to link those two coordinates together by restricting ourselves to a parametric path and trying to integrate over that. So if I get my head out of the way and start drawing some coordinate axes, what you'll see is if we have some curve here, C, and we have some initial point, let's call it R naught, and some final point, let's call it R1, that what we're looking at here is the integral. Sorry, I'm getting ahead of myself. I don't even want to write the integral just yet. I want to look at a different set of coordinate axes. I'm going to call this the x-axis, and we'll have this as the z-axis, and assume we have z equals f of x and y. All right, so what we're looking at is translating this function of two variables by taking this path, and we're going to call this path our s-axis. And we're going to integrate over this curve f ds. Now, we've seen ds. We mentioned it back when we were talking about parametric paths and vector valued functions and arc length. And we saw that ds is the magnitude of r prime of t dt. Right, that's just from our discussion of arc length. And so the integral of f ds is simply going to be the integral of f of r of t times the magnitude of r prime of t times dt. And we'll put in t naught and t1 the times at which you hit those coordinates r naught and r1. So the idea here of how to evaluate a path integral is fairly straightforward. It's just a substitution. It looks a little bit messy, but we've seen how to deal with this when we talked about derivatives. You can take a function, you can use function composition to rewrite a function of several variables as a function of t along a specific path, and then from there it's just a matter of integrating. So as an example, let's take a look at a fairly simple function. Let's take a look at f of x and y is equal to x squared plus y squared minus x. And let's take a look at the path along this circle of radius 2 centered at the origin, but not the entire circle. We're going to start here at the x-axis. We're going to continue counterclockwise 3/4 of the way around the circle. All right, and we're looking to figure out, if we call that our curve C, we're looking at the integral on C of f, and I guess I can call it f of x and y ds. So the first thing we want to do is parameterize this path. It is a circle, which means we can actually parameterize it using polar coordinates. That's usually the easiest way. So we'll have x component as r times cosine of theta, or t in this case. So the radius is 2 times cosine of t, and then 2 times sine of t. You could use any multiple of t that you would like, but right, theta equals t or t equals theta is the most straightforward option. Because now our t is just an angle, and in standard position, that starting point is the angle 0, and that ending point is the angle 3 pi over 2. And so, in order to figure out ds, we need to figure out what r prime is. All right, the derivative of cosine is minus sine. Derivative of sine is cosine. And that vector is all well and good, but the thing we need is the magnitude of that vector. And so we'll take the square root of -2 sine t squared, which is going to be 4 sine squared t, and then 2 cosine t squared is 4 cosine squared t. Notice that sine squared plus cosine squared is 1, so 4 sine squared plus 4 cosine squared is 4, and the square root of 4 is 2. So ds is magnitude of r prime times dt. Magnitude of r prime is 4 in this case. All All right, so important things are falling off the screen. So let me come back up here and grab the important things. We have our function, which I'm going to need. Let's put that back down here. We have our vector path. So let's grab that and put that down here. Cannot paste from clipboard. Okay. All right, let's try that again. Grab this, copy, come down here, paste. There we go. All right, and we've got ds still on the screen. So we have everything we need to set up the integral over our curve of f of x and y ds is actually the integral from 0 to 3 pi over 2 of, well, x is 2 cosine t squared plus y, which is 2 sine t squared minus x, which is still 2 cosine t, times ds, which is 4 dt. All right, before we actually do the integration, we can do some simplifying. Notice that we have cosine squared plus sine squared, which is in fact still equal to 1. So 4 cosine plus 4 sine squared is 4. And I might as well just split this into two integrals. So we'll have 16, 4 times 4, times the integral from 0 to 3 pi over 2 dt minus 4 times 2 is 8, integral 0 to 3 pi over 2 cosine t dt. Now we're getting somewhere fairly reasonable. Integral dt is t, evaluate that at the limits of integration. Integral cosine is sine. Evaluate that at the limits of integration. All right, so we get 3 pi over 2 minus 0, which is 3 pi over 2. Multiply that by 16. 16 divided by 2 is 8. 8 times 3 is 24. So we get 24 pi. Let's see, sine of 3 pi over 2 is -1. Sine of 0 is 0. So we get -1. -8 times -1 is plus 8. 24 pi plus 8 is the value of this particular path integral. All right, let's take a look. While we're at this, let's expand our practice out to 3 dimensions. So how about a function f of x, y, and z given by x squared plus y squared minus z? Kind of similar to the one we just did, but a little bit different. And let's look at a path r of t in component form is sine t, cosine t, t. For t between 0 and 2 pi. All right, this time We're being given the parametric path instead of having to try to interpret it on our own. The reason for that is that it's in 3 dimensions, and trying to understand a graph in 3 dimensions is sometimes very challenging. The best way to understand a graph in 3 dimensions is to plot it in software that will let you move the graph around. And in order to do that, you need to have the equation in the first place. So kind of easy mode in that regard. But the process from here is going to be just the same. We're looking for the integral over this curve of f ds, f of x, y, and z ds this time. And again, the whole idea on this is that we are looking at this function. It's a function of 3 variables. We're taking a path through space to get to this function. And we are just cutting out that path and unraveling this function. And the path that we're taking is going to be a spiral. It's one full loop that is raising up on the z-axis as it wraps around. So we can visualize what's happening. We can think about that story, but the math is just going to tell us that ds is the magnitude of r prime of t dt. And since r of t is sine cosine t, that means that r prime, well, the derivative of sine is cosine. The derivative of cosine is the negative of sine, and the derivative of t is 1. So the magnitude here is going to be, well, cosine squared plus sine squared plus 1 squared. Cosine squared plus sine squared is 1. 1 plus 1 is 2. So the magnitude here is square root of 2. Then from there, it's just a matter of plugging in. T goes from 0 to 2 pi. Our function, x squared plus y squared minus z. Plug in x equals sine of t. Plug in y equals cosine t. Plug in z equals t. And then ds is square root of 2 dt. Sine squared plus cosine squared is still 1. So we've got 1 minus t dt. The integral of 1 minus t is t minus 1/2 t squared. Plug in 2 pi. You'll get 2 pi minus 4 pi squared over 2, which is 2 pi squared. Plug in t equals 0, you get 0. So in fact, that's all we got. Square root of 2 times 2 pi minus 2 pi squared. 2 pi square root of 2, 1 minus pi. If you want to factor it out, I don't know if that makes things better or worse. You could also multiply it out. I still don't know if that makes things better or worse, but that's what we've got. Let's take a look at one more before we wrap up for the day. And in fact, what I want to look at is the same function, x squared plus y squared minus z. And a path here given as sine of t over 2, cosine of t over 2, t over 2 for t between 0 and 4 pi. So what I would like you to do, first of all, is compare this path to the path we saw in the previous problem. Verify for yourself that I have reparameterized the exact same path. And reasonably speaking, we should get the same thing out when we integrate over a path, no matter how we parameterize it. So that's what I'm really asking you to demonstrate here. We have changed the way we express the path. But if you graph this function and you graph the path from the previous problem, you should see that they are the exact same path. And the endpoint going from 0 to 4 pi versus going from 0 to 2 pi means you're taking the exact same portion of the exact same path. But work through this, ignoring that, and then when you get to the end, check your result, make sure you get the same solution that we got before. If you do, it's a sign that things went well. If you don't, it's a sign that something is not quite right here. Always nice going into a problem knowing what the solution should be. But take a couple of minutes, see where you can get with that, and I'll see you in the next video.